Today's video is section 5.1. This section is called Cost, Area, and the Definite Integral. In chapter 5 we learn about the second main quantity of calculus. In other words, we're going to learn about something called an integral. We'll get there. But we're going to start by thinking about cost a little bit more. In a previous section, we talked about cost, and at the time we wrote down some formula. It was probably a polynomial for the total cost C to produce some good, some amount of some item or some unit. And then we used the letter Q to represent the number of units of that particular good that the company made. So if we were given, in that section, when we were given a formula for the cost, if we wanted to, and we did this a couple times, we could compute the marginal cost, and remember that the marginal cost was the derivative of the cost function with respect to the number of items. So we computed dc dq. I'm going to talk a little bit about example 1 from the text. I won't do exactly what they do, but I'm going to use the same numbers. So in this example, instead of knowing the actual cost, perhaps a company only knows the marginal cost and to produce some item. And maybe the company only has limited information. In other words, maybe the company only knows the marginal cost to produce an item at certain production levels. And that's what's given to us in the table here. So I'm assuming that we're producing some amount of a good, and then we're given some data. Okay, my marginal cost to produce 0 cases is $8 per case. If I produce 100 cases of whatever this good is, the marginal cost is less, it's $6.23 per case, etc. So if we're given production level, number of cases, and we're given these marginal cost values, and remember the units for marginal cost are cost units divided by quantity, so dollars per case. If I have this information, I can recover cost, or total cost. And the way to do it really, as if you think about the units, is just to multiply, right? If I do the marginal cost times the quantity produced, or the production level, right? In terms of units, this would be dollars per case, and then I'd be multiplying by number of cases. And so the cases units would cancel, and I would just be left with dollars, which is what I want as my units for the total cost. The problem is, as we can see in this example, is that multiplying marginal cost times quantity only gives you cost if the marginal cost is constant. But here, as we can clearly see in the table, the marginal cost varies depending on my production level. So I can't just multiply like a single marginal cost number by the production level in order to recover cost, because the marginal cost is varying. So the problem that I'm going to solve right now is I'm going to try to estimate the cost, right, estimating here, to produce the first 400 cases. In the book they do the same kind of calculation, but they estimate the cost to produce the first 600 cases. And the idea is quite simple. What we're going to assume here, because we're only given limited information, right, I only know the marginal cost at 7 different production levels. But what I'm going to assume, let's just focus maybe on this first little bit here. As my production goes from 0 to 100 units, I might just assume that the marginal cost is $8 per case over that entire production batch from 0 to 100. And so the marginal cost is constant. I'm going to assume it's constant as my production goes from 0 to 100. Likewise, as my production goes from 100 to 200, I'm going to assume here, maybe, that the marginal cost, I'll just abbreviate it MC, I'm going to assume that the marginal cost is $6.23, $6.23 per case. As my production goes from 200 to 300, I'll assume the marginal cost is constant at $4.92 per case, etc. And so, if we assume that constant marginal cost for each batch, 0 to 100, 100 to 200, what we can do is multiply for each batch. That'll give us a cost to produce that batch, and then I add up those costs for the number of batches that I care about. Right, so here, right, going from 0 to 100, right, the cost would be, what? $8 per case times the number of cases. So, how many cases are we talking about? We're talking about $8 per case times the number of cases, and we're talking about 100 cases here. So we'll do $8 per case times 100 cases. And so this gives us a cost of $800 to produce that first batch. For the next batch, going from 100 to 200 cases, the cost would be $6.23 per case times the number of cases, and the number of cases again is 100 cases. And so that gives me a total cost of $623 for that batch, etc. So if I want to know the cost to produce the first 400 cases, right, I can compute the cost like I've been talking about for each batch separately, and then I add up those costs. So here's what this total cost calculation will look like. So this is total cost for the first 400 cases. I do the calculation. 8 times 100 plus 6.23 times 100 plus 4.92 times 100, and then plus one more, right? To go from 300 to 400, we're assuming the marginal cost is $4.07 per case, and so that's my last one that I have to add on, 4.07 times 100 cases produced, and then I add all these up. So this is 800 plus 623 plus 492 plus 407. I'm not feeling like doing this calculation in my head right now, so I'm going to pull out the calculator and just see what the total cost is. So 800 plus 623 plus 492 plus 407 is $2,322. All right. So this is an estimate for the cost to produce the first 400 cases. Now, we might estimate this a different way, right? If we look back at the first batch, having production go from 0 to 100 cases, what we just assumed was that the marginal cost was going to be $8 per case over that entire batch. But maybe, because I see at the end of the batch, my marginal cost has gone down, right? Maybe I should assume that the marginal cost was $6.23 per case over the entire batch. Right? In other words, maybe instead of using the 8, I should multiply the 100 by 6.23. Going from 100 to 200, maybe instead of using 6.23 as the marginal cost there, maybe I should assume for this batch that the constant marginal cost was $4.92, etc. And so this is a different estimate, using what we can think of as like the other endpoints of the interval. Okay, here's our calculation. $6.23 per case times 100 cases for the first batch, plus $4.92 per case for the next 100 cases, plus $4.07 per case for the next 100 cases, and then for the last of the first 400 cases, we would add on $3.68 per case times that last 100 cases. If I add up all of these numbers, this is 623 plus 492 plus 407 plus 368. Notice that they're different numbers this time, right, than the previous calculation. And the approximate, the value that I get here for the estimated cost is $1,890. So I'm getting two different numbers for the total cost of producing the first 400 cases, and neither of these numbers are probably exactly correct, but I'm just estimating the total cost. And so what the company, if this is all the information they have, what the company would make sense to assume is that the cost is somewhere between these two numbers. We can think about both of those calculations graphically. So here, the blue curve that I've sketched is a marginal cost curve. An example of a marginal cost curve that could have given me that data from the previous table. In other words, right, the dots here are just the points defined by the table. When production is 0, the marginal cost was $8 per case. When the production level was 100, the marginal cost was $6.23 per case, etc. So if I look at this first calculation, I'm going to run it over here. It's 8.00 times 100 plus 6.23 times 100 plus 4.92 times 100 plus 4.07 times 100. I can think about each one of these products as an area of a rectangle. In particular, I know that the area of a rectangle is length times width. And so from 0 to 100, right, this delta Q, it's a change in quantity. That distance, or that width, is 100. So I can take this little segment here as the base of a rectangle, right? So here's the width of a rectangle. And then I'm thinking about rectangles, so I'm thinking about 8 as being the height of the rectangle. Well, in my picture here, a height of 8 is all the way up to that data point. And so making a rectangle with width 100 and height 8, here it is. The area here is 800, and that's the first term in this summation. Okay, the next term in the summation is we can also think about it as an area. The width is still 100, this time the height is 6.23. Well, here's width 100, from 100 to 200, and then a height of 6.23 is this height right here, 6.23, up to the curve. So here's a second rectangle, whose area is exactly the second term in my summation. Likewise, this dot is at a height of 4.92. The width from 200 to 300 is 100, and so the area here of this third rectangle is 4.92 times 100, the third term in my summation. And then lastly, here's a height of 4.07. The distance from 300 to 400 is 100, and so the area of this fourth rectangle is the fourth term in my summation. So what this leads us to is the question of how do we compute area under a curve? Okay, and so the blue curve that we started with here is a curve, and now I've created some rectangles. The rectangles go above the curve, and so the total area of those rectangles doesn't exactly tell me how much area is under the curve and above the q-axis, but it's an approximation, it's close. Okay, if I have some other curve, maybe like y equals x squared, I might, for some other problem, I might need to know, or I might want to know, what the area under this curve is from 0 to 1. Right, that shaded area. And so why might I want to know that? Well, these areas here, right, the sum of these areas came from my total cost calculation, and that total cost calculation, this one right here, only estimated the cost. It wasn't actually the cost. And in order to make that estimation, I had to assume that my marginal cost was constant. That's why I have like these fixed heights for the rectangles. But that's only an estimate, only an approximation. And so if I wanted to actually get a better sense of what the total cost was, what I should do, and this will maybe make more sense in a minute when I show you another picture, is that instead of looking at production from 0 to 100, maybe I could take like a narrower little rectangle here. Maybe I could think about production from 0 to 50 if I had that data. And if I could do that, then I would be getting a more accurate picture of what the total cost was. And so it can be shown, and they talk about this in the text, that the actual total cost, not the approximate cost, the approximate cost is the sum of these rectangular areas, but the actual total cost is the actual area under the curve. Okay, so calculations for total cost actually do require us, if we think about it in this way, they actually do require us to find area under a curve. Actual area under the curve. So, okay, this time, right, we're starting to think about this new example, y equals x squared. Here it is from 0 to 1. And my question was, what is the area under y equals x squared from 0 to 1? Okay, how do I try to find this? Or how do I even go about finding it? Well, they talk about it in the book, and they introduce some notation that's a little bit hard to swallow at first. They talk about Riemann sums. But the idea is actually quite simple, even though it's elegant. The idea is to first approximate the area of the region by finding areas of rectangles. And then the interesting thing to notice is as you take more rectangles, the widths of the rectangles get narrower and narrower, but with the increased number of rectangles and the fact that they're narrower and narrower, the approximation gets better and better to the actual total area. And here's where we can look at the slide on the front board. All right, so I'm looking from 0 to 1. My quadratic function here is y equals x squared. That's the black curve. And now what we're looking at in pink or red or whatever that color is, we're looking at some approximating rectangles. Right, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 approximating rectangles. Since these rectangles are rectangles, I know how to find their areas. Right, I do the width times the height. The height is always determined by some value of the function, right? Because I always go from the x-axis up to the curve. And the interesting thing, like I just said, is as I make the number of rectangles go up, as I increase the number of rectangles, it's still an approximation, but this white space here, the space that I'm kind of missing for the actual area, becomes less and less, right? And so when I have like 100 rectangles, I think I'm at about 100 rectangles, right? The difference between my actual area and the area of the rectangles is really quite small, right? It's like 0.005. It's only off by 0.005. So this observation leads us to a definition of area. The definition is in your book, and this is the rough idea behind it. The area under a continuous positive function, y equals f of x, over the interval AB, say, the closed interval AB, is the following. They call it A, and it's the limit as n goes to infinity, where n is the number of rectangles, of f of x1 delta x plus f of x2 delta x plus et cetera, plus f of xn delta x, where the delta x is the width of one of the approximating rectangles. So delta x is b minus a divided by n. Okay? So like I said, this is in your book, but n is the number of approximating rectangles. The fact that we have a limit here is because we're letting the number of rectangles increase, right? And so limits may or may not exist, but it can be shown that if our function is nice enough, in particular here, if it's continuous and positive, which is more than we actually need for the function, but in that case, the limit will exist. And whatever that limit is, turns out to actually be the area, the exact area underneath the curve. I'll do one example which is similar to a problem that I want you to do for homework. And it's going to be to approximate the area under y equals x squared from 0 to 1 using some number of rectangles. If we look at back to the front board before getting into this example, let me decrease the number of approximating rectangles for us here. This approximation right now is using left endpoints of the subintervals in order to get the heights. And so that corresponds to our first approximate cost computation. The second approximation that we had for the cost, remember, used the other marginal cost, the other endpoint. And so that would be using the right endpoint of each subinterval. You notice that the rectangles change, and that should make sense because now instead of using the left endpoint to get the height, I'm using the right endpoint to get the height. And so now all of my rectangles are taller. It doesn't matter which rectangle you use, provided that the area or the limit exists. So for this example, let's try to approximate the area under y equals f of x equals x squared using, say, 6 approximating rectangles, and let's use right endpoints. All right, so that we have something to look at. Approximate the area under y equals x squared from 0 to 1. Here's 0, here's x equals 1. Here's a graph of the function, y equals x squared. That's also f of x. And now I want to use 6 rectangles. So that means I'm dividing up my interval 0 to 1 into 6 pieces. Okay? That means, what does that mean? divided into 6 pieces of equal width, which isn't a necessary assumption, but it's typically made. So I divide 0, 1 into 6 subintervals of equal width. Each of the widths, which is delta x, would have to have length 1/6. Right? Delta x is b minus a divided by n. The a in this case is 0, the 1 is b, and then the n is the number of rectangles, and for this example that's 6. Right? So my width, delta x, is 1/6. So here's 1/6, here's 2/6, here's 3/6, 4/6, 5/6. Okay, those sixths divide the interval 0 to 1 into 6 equal pieces. And now, if I look back at the statement of the example, I'm supposed to use right endpoints. I'm using right endpoints to get the height of each approximating rectangle. So 1/6 is my first right endpoint. I go up to the curve. That's my first height. 2/6 is the next right endpoint. I go up to the curve. That gives me the height there, etc. And for the last right endpoint, it's actually 1. Up to the curve and over gives me the height. So you can see my 6 approximating rectangles now, and I need to add together their areas. So this area, the actual area, is approximately going to be the summation of the areas of those 6 rectangles. For the area of this first rectangle, I know that the width is 1/6, and to get the height, what did I do? I went up to the curve, so I had to plug 1/6 into the function. That means that this height right there is 1/6 squared, right? Because my function is the squaring function. So the area of that first rectangle is the height, 1/6 squared, times the width, which is 1/6. For the next approximating rectangle, again the width is 1/6, and then to get the height, I plugged 2/6 into the function. So this second height is 2/6 squared. Again, because the squaring function is the function I'm working with. So we would have the height, which is 2/6 squared times 1/6. And then you continue this process for all 6 of the rectangles. You get plus 3/6 squared, that's the height of the third one, times the width, which is 1/6 again, plus 4/6 squared times 1/6, plus 5/6 squared times 1/6, and then plus 6/6, or 1 squared, times 1/6. All right, doing this calculation, you can use your calculator if you like. It'll give you an approximate area. I'll do it real quick, hold on, 1. I believe you should get about 0.421